Yep. I want to get started. Let me get my video going. Hey, look at that. Quickly, today, let me spotlight this. Hold on. Today we're going to go over 2.6 domain of functions, and then 2.2, which is my probably favorite titled section, more on functions. And then remember, Monday is Labor Day. We will be off on Monday, so I won't see you guys for another week. Okay, I got an email from a student that had a question, and I'm excited because I get excited over those kind of things. So, Chastity, I told you to ask me in class, and thankfully you obliged. Or you're about to oblige, right? I should say it that way. Which one was it?
Well, what I think I'm actually struggling for the most part, because I have factoring like down. I'm good at that.
Perfect.
But I'm struggling with the square root stuff.
Yeah, the square root method. Yeah.
I mean, I'm not struggling with the method. You know,
okay.
So I'm struggling with square roots in general. That was my weak point.
Oh, like simplifying them?
Yes, and
Like if you found an example for me and you're like, this is what I want.
Okay, I'm gonna go back to the homework problems that I have.
Okay.
The 1 through 33, I'm great. I got the factoring down. It was as soon as I got to that next section, like 17, and even 19. I don't know how I missed the whole. I know that if you have to take the square root of a negative number, you're supposed to automatically pull the I out.
Yeah.
But for some reason, I don't think I came out with good grade last semester, but I missed that somehow. Like I didn't master it.
Well, okay, so let's look at like let's look at 17. Why not? So if we did yes. So we've got 5x. This is 17 on page 160, guys. 5x squared plus 1. Can you guys see that? Yeah. Equals 51. And it says to solve this by the square root method. I'll tell you, there's a huge indicator to use the square root method because there's no x value. It's only x squared. Do you see that? So when there's only an x squared, my brain automatically thinks, hey, this is going to be an easy square root method. Okay?
Okay.
So then I'm going to subtract the 1 on both sides because my goal now is to get that x squared by itself. Divide the 5, and I wind up with x squared equals 10, right?
Okay.
You see where maybe you were kind of going?
I definitely see what I did wrong.
Right? Yeah.
I was automatically trying to do that that formula with negative b plus or minus.
Oh, no. Okay, that's a different thing. That is that's the quadratic equation. So that's a different section, or a different type of solving, I should say.
Okay, I definitely see what I did wrong there. Okay.
Oh, good. Okay, so now I'm going to finish this one up though. I'm going to take the square root of both sides, but when we take the square root, we have to add a plus or minus, right? Now 10 we can't simplify. It's just 5 times 2.
Yeah, so that throws me off too. So that's
okay. So I can't simplify 10. 10 is only broken down into 5 times 2, right?
Mm-hmm.
And neither one of these can go any further, so there's no pairs. So I'm stuck with 10. Okay. So then the answer is going to be x equals plus or minus square root of 10.
Okay, that makes sense.
Does that help?
Yes.
Now go back and try it and see if like now it all just kind of clicks together.
Yeah. Oh, I will. I'll go back and practice some more. I think that's all I was struggling with. It. I was trying to use that formula, and
yeah, you were getting wires crosshair or crosswire.
Okay.
Yeah, you were getting 2 wires crosswire. What is it? I know I'm saying it the wrong way, but you're getting them tangled. That sounds like the wrong way to say the right thing.
Okay. I think I'm good then. Thank you.
Perfect. No problem. I'm glad you asked. Any other questions about 1.5? I didn't assign homework for 1.7. That was just a kind of a review over interval notation, but we used it in 2.1. If you did the homework in 2.1, you saw that. So were there any questions from 2.1 or 1.5 before I get to rocking and rolling? First on 2.6. So I'm going to go ahead in my book a little bit. And so we're going to start on 2.6, which is domains of function equations. Okay. Look, there's two main things that can really mess up the domain of an equation. I'm going to just flip over so I can steal examples from the book. And I call them my two red flags. Okay. I've got two red flags whenever it comes to this. Look, if I don't have a red flag, it means my domain, remember my x's, it's where the x's exist, right? It means that my x's can exist anywhere. Okay. And we'll get to the red flags first, and then I'll show some examples on when we don't have that issue. Okay. I can tell you right now, we're not going to get all the way through 2.6 and 2.2 today. Okay. And that's fine. We'll finish up 2.2 on Wednesday. And remember, the test is going to be the following Monday. Okay. And we'll have time to review a week from today. Okay. We'll finish up 2.2 next week, and then we'll review on the rest of that day. And the test will be Monday. So we're going with the schedule. If you're looking at the schedule Blackboard, we're right in line with it. Okay, so back to this though. There's two red flags. The first red flag, maybe I can draw a little red flag here because I do love this. Okay, first red flag is x's in denominators. Okay, x's in denominators. I'm going to give you an example of a domain function with an x in the denominator. So f of x, remember that's just function notation, equals 2 over x minus 3. This is a good example of an x being in the denominator. So my senses are going off because of this x right here. Okay. Not that he or she shouldn't be there, okay? But I've got to be careful that they're there, okay? It's one of those things. Look, we might not have any problems. We might not have any red flags, honestly. But this is an indicator that we could have an issue. And the way, really where this red flag comes from is that you can never divide by 0, right? We can never, ever, ever divide by 0. If you remember back to slope, if you ever have a division of 0 with slope, it winds up being undefined. We don't know what to deal with it. We're actually going to go over what happens in a few weeks or about a month on what happens when we do have a 0 in the denominator. Actually, when we get to 2.6 is when we're going to look at it. Okay. But for now, I'm just giving you a taste. So we don't know how to deal with undefines. It doesn't have a cool name. So we're just going to make it where our x does not exist where x is undefined. Okay. I should say where the function is undefined. Now, the way we do this, we actually set the whole denominator not equal to 0. And this is how you find the domain, okay? We are finding the domains of this function, or the domain of this function. So you set the denominator not equal to 0. And then you solve it out. Look, x minus 3 can't be 0, x plus 3 on both sides. X cannot be 3. That is our domain. X can be anything it wants to be. Okay, it can be pizza. It can be an apple. I don't care what it wants to be, but it cannot be 3. Okay. Now remember, we don't notate mathematical logic like this. Okay. Remember at the end of that 1.7 little lecture, we went over the set notation, the graph notation, and the interval notation. Well, I'm going to do all three of those real fast just to show you where our interval notation is coming from. If we had a number couldn't be, or x couldn't be a number, on the number line, that meant, we got infinity, 2, 1, negative infinity. It meant that, look, x can be anything to the left of 3 and to the right of 3. So we use that union notation. We said x can be anything. Oh, hold on, give me 1 second, guys. Oh, there we go. X can be from negative infinity, we use parentheses on infinities always, to 3. It gets a parentheses because we can't be 3. Union, because remember that meant or. So X can be anything from negative infinity to 3, or it could be from 3 to infinity, and I'm running out of space. Okay, and it gets a parentheses as well. So this would be our domain. This is where the x's exist. Or you could say this is where the x's can exist, right? That is our domain. Because now we have a graph going on here. it's not just a before in that last lecture we had like groups. Remember, did I do the pet example with you guys, right? So we had like the students were the domain, and then like the type of pet they had was the range, and we just listed out the students as our domain. Well, in this example, it's different because this is a graph, and I'm going to kind of show you what this graph looks like. What happens, and we're just not there yet. If you've seen it before, that's fine. What we have is we've got something crazy happening at 3. It's so crazy, we put a dashed vertical line there, okay? Just to indicate, look, we cannot be that coordinate. And then let me use, I'll use black, that's not a big deal. This line looks something like this. Let me think, it probably goes down. Down like that, and then it jumps over, and it looks like that. That's what f of x looks like, okay? And you can kind of see, look, if I chose an x value, I'll always have another y value because of these arrows, okay? If I chose an x value, I would always have a y value because of the arrows going forever, except at x equals 3. I've got this fence. We'll talk about what that fence means actually on the next test, okay? So don't worry about the fence. All I really need you to know now is how to get this domain. If we see the red flag with an x in the denominator, set the denominator not equal to 0 and solve it, okay? Solve it and then put it in interval notation. So I'm going to give you an example, and I want you to try it. We're going to keep it basic, okay? I'm going to keep it very similar to that one, just so we can do this on our own. Let's say we had g of x here, and it was x minus 5 over x plus 7. And I'm going to give you a little hint. The numerator does not matter. I want you to find domain of g of x. And that numerator could have had a dragon written on it, and it doesn't matter. All we worry about is the denominator. So find that. I'm going to pause this real fast so the video. Okay. So look, the only thing I care about is this x plus 7. And I know x plus 7 cannot equal 0. So I subtract the 7 over, and I get x cannot equal negative 7, right? So on the interval notation, I'm going to go straight to interval notation. X can be anything it wants to be. It just can't be negative 7. So negative infinity to negative 7, union negative 7 to infinity. This would be my domain, okay? That's going to be my domain. Now, I'm going to talk about the next red flag, and I'm going to go back to other examples of this, okay? So then I can kind of mix them all together. But I will get back here. I'm gonna make this one a little bit harder because we need to go over a little deeper here in a second. Okay, the other red flag is even roots. Okay, so this is oh, wait. Did I try? Ah, yes, I did. Okay, hold on. The second red flag. Okay. The second red flag is even roots, and you can pretty much write square root if you wanted to, but even roots in the equation. Okay, even roots in the equation. I'll give you an example of this. If I had h of x and it equal, let's say, the square root of 2x plus 5. Why not? It doesn't matter what's underneath there. What matters is we have a square root. This is a red flag for us, okay? I've got an even root. And you know, like before, the x's in denominator, the reason that was a red flag was because we could have a denominator of 0. Like if we quickly kind of go back to this example, if I plug negative 7 into this function, like if I plug, which I'm not supposed to, right? But if I do, I'd have negative 7 minus 5 over negative 7 plus 5. I'd have negative 12 divided by 0. This can't happen in mathematics. We don't know how it happens, actually. We don't know what happens when we do it, okay? So that's why we have that red flag. That's why x can't be negative 7. Over here, though, it's a little different because you could be a negative, or you can be a square root, right, of 0. The square root of 0 is just 0. But in the real world, which our domains only exist with real numbers, in the real world, with real numbers, we can only take square roots of positives and zeros. We can't take square roots of negatives, right? You told me that earlier, right, Chastity? I know if I take a square root of a negative, it's imaginary. Well, our domain can't be imaginary. So if we see even roots, all we have to do is put whatever's underneath that radical. So for us, it's 2x plus 5. And we're going to state that that has to be either positive or it has to be 0. And the way you do that mathematically is say that it has to be greater than or equal to 0, right? This statement in mathematics means that whatever we put in here has to either be 0, which is fine, the square root of 0 is 0, or it has to be greater than 0. It has to be a positive number, okay? That's what that is stating. So now, if you're like, whatever, just tell me what steps to work. The step is stick whatever's underneath the radical, or the even root radical, greater than or equal to 0. Now, guys, it has to be even root. If this was a cube root, wouldn't matter. We wouldn't have a red flag, actually. We'll go over one of those here in a little bit. So let's solve this out now. If I want to solve this, I subtract the 5 on both sides. 2x plus 5. Oh, wait, I already did that. 2x is greater than or equal to negative 5. And then I would divide by 2. And I would get x is greater than or equal to negative 5 halves, right? Which is fine. Now, this one's different. It's not that x can't be a single number. X has to be any number as long as it's greater than or equal to negative 5 halves. Like if we drew this on a number line, negative 5 halves is out there somewhere, and we go from infinity to negative infinity, right? And we're saying, well, usually I've been writing these underneath, haven't I? That's fine. But we're saying it can equal negative 5 halves, so it's going to be a closed circle, but it's also got to be greater than 5 halves. So it would look like that, right? So if I'm going to write that in interval notation, this is going to be bracket, because I can be equal to the negative 5 halves to positive infinity. Whoop. Oh, I'm going to set that infinity. Parentheses. This would be my domain. This is where my x values exist, okay? I'm going to draw this graph too, just to kind of show you, because it's a little easier graph to see. And if you did the homework, you probably saw one like it. If I drew this graph, negative 5 halves is what, negative 2.5? This graph actually looks something, I'm going to draw one that kind of looks, it's not going to be just like it, but it'll have the same domain. It looks something like this, okay? It looks something like that. Now imagine that point is right above negative 2.5, okay? And so what's happening is our domain is starting at negative 2.5 here, and it's going forever because of that arrow, okay? That's what this interval is saying, okay? Our x's are starting at negative 2.5, and they're going forever, okay? Questions other than, I probably just need to see a few examples of that, and then it'll start clicking. Okay, yeah. Let's look at a few more examples. So let's say same kind of thing. I want you to try this one. Let's say we've got f of x equals the square root of negative x plus 3. Why not? And I want you to find the domain here. Find the domain of f of x. I'm going to pause it again. Okay, so let's see. You had to remember a rule about solving inequalities, or you've got this one backwards. So negative x plus 3 has got to be greater than or equal to 0. When we solve this one, we subtract the 3, and we get negative x is greater than or equal to negative 3. Now look, if we want to get rid of that negative, you either multiply by -1 or divide by -1. But because you have an inequality, you have to flip it. So I like dividing by -1. I'm sure it's just how I learned it. But when I do that, x is greater than turns into x is less than. So I wind up with x is less than or equal to 3. I chose that because it was kind of a trick just to see if you did it, and that way you notice that you're doing it wrong, okay? So x winds up being less than or equal to 3. And now if I want to write that in interval notation, what this means is X can be anything, including 3, but it's got to be less than 3. So it's going to look like this, negative infinity all the way to 3, but I'm going to include the 3, okay? These, mean the same thing, right? Just written 2 different ways. Okay.
So is that are there only the 4 sets that we notate this way, or are there more? Are we going to
What do
learn
you
more
mean by
later?
4 sets?
In my notes, I have 4 different ones, like X is greater than X greater than.
Yeah, now there could be honestly like an unlimited type of ways we do this. But so we have to really go back to how the answer is, Chastity.
Okay.
So, and so you kind of have to think, and if you want to think of the number line, typically students at first when they're learning this, like to think of it on the number line and then bring it to the interval. So like, if you want to think, okay, X is less than or equal to 3, if that was a number line, we got 3 here, negative infinity, 4, 5, 2, right?
Yes.
And then I can be 3, but then it's anything to the left of that. And then go to this. That's fine too. Does that help?
Well, sort of. It's just the parenthesis in the bracket. I guess I just need to write that in my notes. Like,
okay, yeah. Here's what I would write down. First off, infinities always get parentheses because we can reach infinity, right?
No matter what. Okay.
No matter what. Doesn't matter, right? But if we include the endpoint, it's a bracket, okay? And see, for this one, because it could equal it right there, that means I know I'm going to use a bracket because it's included.
All right.
And then if we don't include it, though, it's got to be a parentheses. It's got to be a parentheses. So I'll tell you, if this one, I'll use a different color. If this was like X is less than 3, this would be negative infinity, parentheses always on the infinity. But this one would be a closed parentheses, or I'm sorry, a parentheses.
Okay, so I have that one in my notes, so.
Yeah, and it's because X can't equal the 3, right? It's got to be anything less than that. It could be 2.9, it could be 2.9999999. It just can't be 3, right?
And then the U basically just means or. If you have,
it's an or
if you're going to have 2.
Yeah, this time it didn't happen, right? Because it was only one interval. If you go back to that other example, we had 2 intervals, right? We got this interval, we had this one. That's why we needed the or statement.
Okay.
Yeah, no problem. Okay.
Thank you.
Yeah, no problem. Nathan, are you saying something?
I said literally just answered the question I had.
Oh, okay, gotcha. So let's look at a few more. Let's look at one that just doesn't have either of these red flags, right? So if I had a function like g of x equals like a nice quadratic function, 2x squared plus 8x minus 1. Oh, this is a beautiful quadratic, right? If I wanted to solve for like X-intercepts, I'd set this equal to 0. I'd use a quadratic formula, be done. Oh, we're not there. We're not there. But for now, we're just in the domain. I'm going to ask you, what's the domain of this guy? Or girl, it doesn't matter. What's the domain? And you're going to go, okay, wait a minute. Let me go back a few slides here, manually go back a few slides. This doesn't have a square root, right? All these things are squared. This doesn't have an x in the denominator, like over here. So it doesn't have a red flag, right? I think this means that x can be anything. And you're right, okay? X can be anything it wants to be here. There's no red flags. You'll never have a division of 0 here. And you'll never have an imaginary number pop up because there's no square roots. So guess what? The domain is all real numbers. Now, the way we notate all real numbers, there's a few ways in mathematics. Actually, the first way is it looks kind of like a paragraph indentation thing from English. You can use an R with an extra stem. I'll use this a lot in my lectures because it's just a quick way to say all real numbers. But an interval notation, which will pop up on the test, it's going to be negative infinity to infinity. Those 3 things mean the same exact thing, right? X can be anything. It can be anything from negative infinity to positive infinity. Okay? Guys, questions, comments, concerns? But look, no red flags. Okay? I'm going to do a few more that have just no red flags that your book's going to try to get you on, okay? And it's a really easy question, right? Because there's no math if there's no red flags. Another one would be if we had a root that wasn't even. So if I had, let's say we've got z of x. Z sounds cool. And I've got the fifth root of 2x plus 7. And I know what you're thinking. You're thinking, wait a minute, that's a radical. And that radical, earlier when we did an example with a radical, we had to set the thing greater than or equal to 0 and solve. But the red flag was for an even root, right? This is a square root. We just don't write it when it's squared. But this is a square root. That's when we have to go through the rigmarole of the red flag issue, okay? A fifth root, though, that we're dealing with, let me zoom back over here. This one is a fifth root. It's different because it's not an even root. So because it's not an even root, guess what? This domain is just all real numbers. And it's because imaginary numbers come from taking square roots, fourth roots, sixth roots, okay? In this class, we're only worrying with square roots, okay? So don't get freaked out when I said fourth root, sixth root, and stuff like that. We're going to stick to square roots because we know those already. But the domain here is all real numbers because it's an odd radical. It's an odd root, I should say, or index, depending on how you learn that. Okay? Questions? Good. Now I'm going to draw one, and you're really going to be upset with me on this one. But we have to go through on why this one is not a what's the word? A red flag. So we've got g of x equals, let's say 2x over x squared plus 9. Okay? And you're going to go, hey, Mr. Sherm, that's a red flag. I see an x in the denominator. You told me a few slides back, x's in denominators mean red flag. So therefore, I know I've got a red flag. Well, you could have an issue. And this is called, I forgot what the word is now for this, but we've got to check it. So let's check to see. I'm going to follow the steps here because I do have an x in the denominator. This thing can cause the issues on the domain. But let's see if that actually happens. It's not. But I want to show you why it doesn't. If I've got x squared plus 9, remember if the x is in the denominator, that whole denominator I'm going to set not equal to 0, right? That was that first red flag. I just set the whole thing not equal to 0. And then I solve it out. Actually, I want you to solve this one out because it's a good practice on solving quadratics. It's a good practice on what Chastity asked me at the very beginning of class, okay? So try that real back here, recording. If you subtract the 9 on both sides, you get x squared can't be negative 9. Now look, I'm going to pause right here. We're going to think about this, okay? X squared really equals negative 9. We're solving the same as an equation. Is there any x value I could plug in where I square it and it turns negative in the real world? No, there's not, right? In the real world, this would never happen. You can't square a negative. If you square a positive, you're going to get a positive. If you square a negative, you're going to get a negative. So I know right here, I'm not going to have to worry about it. So I'm going to keep going though for class. If you square root both sides, you wind up with plus or minus the square root of negative 9, right? So you end up with x cannot be plus or minus 3i. Now I'm going to go back to what the question was. We're trying to find the domain, right? Oh, I know the word I was trying to remember. Whenever we have this issue with an x in the denominator, what we're really finding are restrictions on the domain, right? So if you go back, like I'm going to go back real fast to this example, what we found was that x equals 3 is a restriction on this domain. It can be anything at once except 3. So it's called a restriction. Now we're going to go back to present day, to this example, and we'll see the only restrictions we found were imaginary. Well, that's fine. Our domain is only in the real world. It's only out with real numbers, okay? So therefore, because my restrictions were imaginary, I don't have an issue on the domain. I don't have a restriction. because the restriction domain is just real. So this winds up being negative infinity to infinity, okay? So I'll write that down here, restriction or imaginary. So really, I have no restriction.
Hey, can you stick the rent out there for the landlord real quick? See the Ziploc bag?
Your thing's on there, Chastity. Okay. That's okay. Yeah. Questions, guys. These are kind of, so these are three functions that just don't have any restrictions. So they wind up with all the same domain. If you don't have a restriction, you're going to have all real number domains. Okay. And it happens. I mean, we'll have restrictions. We won't have restrictions. We'll have that square root issue. So it's got to be anything greater than or less than a number. It's just what happens. So I'm going to give you the homework now for 2.6. And I kind of expect questions from this because they don't all look the same. Let me look at this. I'm going to go back to here. I'll just write it here, okay? So the homework, this is 2.6, and it's not going to be a lot of homework, actually. I might even steal some examples from the book to add those as homework, which is kind of nice because they work it out for you. Let me see here. It starts on page 297, and I want you to do 1 through 8. I'm going to do all these because there's not a lot. 1 through 8, and then 17 through 23. And then I'm going to add some examples on here. Hold on.
Are we doing odds again?
No, I want you to do all of them because there's just not a lot. And then if you want to check your answer later, like if you're not confident on your answer, just ask me in class and we'll go over it. That's not a big deal. So on page 287, you'll see there's 4 examples. And I want you to do examples A, B, and C. Okay? Don't worry about D. It's a little weird. But examples A, B, and C on page 287. And they work those out too, so you can see how they work those out. But I want to add those in for the homework for 2.6. Okay. So now let's get back to 2.2. And I mean, we've only got like 15, we've got like 35 minutes. So that's fine. We won't get to 2.2, but we are definitely going to start 2.2. Like I said at the very beginning of this lecture, 2.2 is one of my favorite titled sections. More on functions. And the very beginning of 2.2 just talks about different kind of identifiers of a function, different things a function can do. It can go up, it can go down, it can be flat. And the very first thing your book talks about is in 2.2 is increasing and decreasing functions and what that means. If you go to page 229, 230 is kind of where it starts. And I'll tell you, there's a kind of a complex definition of where a function is increasing or decreasing. I am not about that. So we're going to go over kind of the easy way to see this. And I'm going to make up a function right here. I'm going to just draw one of these bad boys. We're going to talk visually what is increasing or decreasing. I do this example every semester. I feel like it helps students grasp this. Sometimes I don't know if anything will help, but I'm going to try. Okay. So I'm going to do a very basic quadratic graph. A quadratic graph is either going to go from down to up and then back down, or up to down and back up. Okay. We'll do one that goes up and then down. So the peak is going to be right here at 2, 3. Okay. And we go down forever. Like that. Okay, this is a basic example of a quadratic. I don't know what the equation is. I'm not worried about it, but that's what a quadratic looks like. Okay, so here's the goofy thing I do every semester that I enjoy. If you're going to think of increasing or decreasing, or really where a function is increasing or decreasing, you have to go left to right. Okay, left to write. So I love drawing, okay? So I'm a very visual learner. So I think of someone riding this graph left to right as a roller coaster, okay? Whoop. Grew out my hair for the roller coaster, but you kind of see that person right there is riding that roller coaster left to right, okay? And this really determines where we're increasing or decreasing. You guys would tell me right there, I mean, where he's at, or she, right there, he is definitely increasing, right? He's going up. And then he's going to hit this peak here, and he's going to go down. And it's going to be fun forever, okay? Does that kind of make sense visually? So what's happening is, now look, this is the weird part. He's been traveling up forever, okay? Forever from the left. So forever from the left, he's been going up. And then forever from the right, he's going down, okay? I know you're like, man, you're making this way more complicated than it should be. I am. You're right. You're not lying, okay? But I'll tell you, we always notate, what is this called? Increasing, decreasing, or constant. We'll talk about constant. That's not happening in this section or on this example. But we always notate increasing, decreasing, or constant with the domain, okay? With X values. So for this example, and I'm going to use, we'll use blue for going up, okay? Forever that way, we're increasing, right? I'm going up forever. And then it switches at 2 right here. I'm going to go down forever. Okay, let's see. Down forever gets to be purple. Let's see if it shows up at all. That looks kind of the same, doesn't it? That's okay. But at 2, it switches. And from 2 to infinity, it goes down forever. So on the test and in the homework, you're going to see, hey, given this function, where is it increasing? Where is it decreasing? And where is it constant? Now, we don't have a constant here. I'm going to show you how to state that answer, okay? Well, look, it's increasing. Remember, think of riding the roller coaster. It's increasing forever to the left of 2. So I'm going to say negative infinity. And at 2, but now look, at 2, it is neither increasing nor decreasing, right? For a split second, in an infinite time, it stops, right? And you know, if you've ridden a roller coaster, that's where your gut goes, oh, it's about to go down, right? This is about to get real fun. And then all of a sudden your stomach drops, okay? That point, though, is neither increasing nor decreasing. So therefore, I cannot include it in this interval for increasing. It gets a parentheses, okay? So we're increasing forever to the left. Look, we're going up, 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 up. And then at 2, right here at 2, we switch. We go forever down. So now I'm going to use a purple. 2 to infinity, okay? It switches. Now this graph does not have a constant value. So look, remember, if we do not have a constant or we don't have anything, you can say none. That's fine if you want. But in math, we just make a circle with a line through it, right? That means it's called the null set. And it means there's not a value for X that makes this function constant, okay? We'll do a constant example next. Okay. Any questions other than, that was really complicated. I need to see another example. Great, okay. Throw some more examples out here, and we'll probably just work on examples the rest of the day. Okay, so let's look at another one. I'm gonna ask you more examples out of this one from the last section. So I'm kind of gonna bring in stuff from the last section and this section. Okay, let's start here a little differently. Let's start at -1 I'm sorry, -3, -1. Okay, that's where we're going to start. And we're going to go up until we get to 1, 3. Okay? And then we're just going to flatline. Now, I know that my graph's not perfect, but I'm telling you that's a flat line. That's a horizontal line right there. Okay? It does not go up and it does not go down. Now, I'm going to make this an A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P type question. Okay? But I'm going to start what we've been going over here. So for A, I want to know, we'll call this f of x, if I need to notate it, okay? Where are we increasing? Where are we decreasing? Where are we constant? Okay, where are we increasing? Where are we decreasing? And where are we constant? Now again, I'm going to draw the little guy. He's right there, and he's definitely increasing, right? But then at 1, it changes, right? There's 1. At 1, it changes. Now he's on the most boring roller coaster ever, right? And he's just going flat. And he's upset. Okay, why did he pay all this money to go to this theme park? And he's just riding a flat roller coaster. Okay. So I can tell what we don't have here, though, is decreasing. Do you guys see that? We're going up and then we flatline, so there is no decreasing. So right off the bat, I'm just going to put a null set there. Okay. We don't have decreasing. Now, what's different from the last section, or the last example of this one, is this graph actually starts here. Do you guys see that? So it doesn't go forever down. It starts there. So we start increasing here. Now look, even though I know that coordinate exists, I get that. But with increasing or decreasing, you never include the endpoints, okay? I can't say I'm technically increasing there because I don't know what happened right before it, right? Right before it might, I mean, there's nothing there, but if it was coming down, it wouldn't be increasing there. So I can never include endpoints when it comes to increasing or decreasing. I'm going to write this over here. Never include endpoints. You know, that means brackets, right? We're not going to put them in brackets. Never include endpoints with increasing, decreasing, or constant, okay? Side note, that's important, okay? Never include endpoints with increasing, decreasing, or constant. Okay, so let's get back to this though. What does that mean? That means really, and I'm going to use some colors again, we increased from -3 here to +1, right? So -3 to +1. Remember, we use the x values. -3 to +1, we're increasing. But then at +1, it turns flat lines. Let's see, let's use orange, why not? And we're just going to be flat from here on out, right? From 1 to infinity, we're just stagnant, okay? We're not going up, we're not going down. Again, it's the most boring roller coaster in the entire world, okay? Okay, questions? I'm going to keep going with this to review stuff from the last section. So you just answer these. I'm going to ask them, and then I'll fill it in as I go, okay? So you answer these. I'm not going to go over A, B, C. I need to learn my alphabet. A, B, C, D. Is this a function? Why or why not? That was 1. A, B, C, D. What's the X and Y intercepts? Okay, A, B, C, D, E, F. What is F of 1? I think that kind of covers it. I'm going to check to make sure I missed something. Oh, wait, yeah. A, B, C, D, E, F, G. What's the domain? E, F, G, H. And what's the range? Okay, this is stuff, you know, we went over last section. I got you, Sherry. I'm going to press pause here. Let's go through these. So first off, is it a function or not? You can tell me in the chat if you want to. Is this a function? Yes. Yes, Haven, you are correct. You win all the points. Yes, it's a function. Why is it a function? It passes that vertical line test, right? Remember, if we do the imaginary vertical line and we go across, it's a vertical, it's a function. Now, I already labeled it a function, so I kind of gave that one away. But I didn't think of asking all these things to review from the last section. Okay, X and Y intercepts. Okay, guys, I want to dig a little deeper here. An X-intercept, of course, is always where the line crosses the X-axis. We have an example where this happens here, right? We cross right there. But you have to write the X-intercept, if I ask for the X-intercept, as a coordinate. So this is going to be -2, 0. That is that coordinate right there, okay? We have to write intercepts as coordinates. Y-intercept, so that's the X-intercept. The Y-intercept, though, is up here somewhere, right there. So it's going to be, now for the Y-intercept, the X is always 0. So 0, 2. Okay, so that's our X and our Y-intercept. F of 1, now remember F of 1, what this means, we don't have an equation to plug this in, right? Last time we had equations, we plug in 1 and pop out the Y value. But for now, we know, for this example, we know that X equals 1. And I go over here to X equals 1 and I go up, boom. That coordinate looks like 1, 2, 3, +3. So that's the solution. This is not a coordinate. I know it looks, you're like, yeah, no, it is a coordinate. That's coordinate 1, 3. Well, but it's written in function notation, in equation notation. So I'm asking you, what is the solution when X equals 1? It's a goofy, it's like learning the language part of math, okay? Domain, though, I'll tell you, if you look back now, domain, remember, is where all the X's exist. It's where there's any color line right here, that blue and that orange, because this line starts existing at -3, right? It doesn't exist before -3. Starts existing at -3 and it goes forever to the right. So the domain, now we include it because we got a closed circle, right? So we include it, we use a bracket, -3 to infinity. The range, though, remember, is just where the Y's exist. I'm running out of colors here, but we start existing right here. I called this -1. So we start existing at -1. We don't go up forever. Remember, we flatline at 3, okay? So the range then, now it's going to be included because everything's closed circles. We go from -1 on the y-axis all the way up to +3. That's where all of our y values exist. There's not a y value greater than 3, and there's not a y value less than 3, or -1, I should say. Okay? Man, hey, Mr. Shirley's tying math all together. He should get paid more. Okay? Questions? I'm good. Really, I'm going to kind of stick to this, but I'm going to make different graphs now. And so we're going to have to pull information from different graphs. Oh, I need to, wait, I can include the next topic. The next topic's easy to pop in here now. Okay, let's go back to the question before. Let's go back to this one, and we're going to talk about the maximum and minimums. Where is that one? Yeah, relative maximum and relative minimum. Okay, so a relative maximum or a relative minimum occurs when the coordinate is the tallest or lowest of all the coordinates around it, okay? That's why it gets the word relative. Like this coordinate right here, 2, 3, gets to be called, now it's the absolute maximum as well, but that's not what we're worried about. It's also the relative maximum, because look, if you're standing here, you're taller than the coordinates to the left and to the right, okay? So because you're taller than the coordinates to the left or the right, that coordinate right there would be a relative max. Now, I do not like how this book notates relative max and min. It'll say something like, where does it occur and what is it? The where is the X value, and the what is the Y value, okay? The where is the X value, and the what is the Y value. I'm just not a fan of it doing that, but that's what it's going to say. It's going to say, well, where does the relative max occur? Oh, it occurs at X equals 2. What is the relative max value? Oh, it's Y equals 3, okay? But in the end, it comes from the coordinate 2, 3, okay? It comes from the coordinate 2, 3. This doesn't have a relative minimum because there's not a point where like it switches, and then it would make a relative minimum. Okay, so I know that's goofy, but in the homework it's going to say something like, "Where is the relative minimum?" Let me look in the homework real fast and see if I can find an example. Yeah. Yeah, okay, guys, I want you to look over to number 33 in your homework, and you'll see how it's worded. If you don't have this, I'll kind of graph 33, and we can kind of see what's going on here. So we've got this graph. It goes up to like 4, 1, 2, 3, 4. It goes to the left, and then it's a big U, okay? But at 4, negative 4. 1, 2, 3, 4. 1, 2, 3, 4. And then 5, 6, 7. Looks like that, okay? And then part H states the number, this sounds real fancy, the number at which f, they've declared this f of x, okay, has a relative min. Okay, that's our where question. Where is the relative min? Well, the relative min occurs at right here, right, guys? Because look, if I'm right here, all the coordinates to the left are above me and to the right are above me, okay? So that coordinate 4, negative 4 is the relative min. Now, the number at which f has a relative min, that's the where. So that's x equals 4, okay? A, B, C, D, E, F, G, H, I. It asks, well, what the relative min of f. The relative min of f. Well, that's the what, okay? That's the what question. What is the relative min of f? I hate, that doesn't even sound like a sentence, the relative min of f. I wish I would have written that as a sentence because this is an academic book. But that's fine. That's the y value, negative 4, right? It occurs at y equals negative 4. So that is the relative min, okay? So I just wanted to go over one, and this is a good example of relative min. How they word it, I'm not a fan of how they word it. I don't think it's whatever. I don't get to make the money off this book because of that. But they do word it this way. Blitzer words it this way, and that's just how it is. Okay, so when you come to that, though, realize that's what it's asking. If it's asking what's the number at which f has the relative min, that's the x value. If it's saying, well, what is the relative min? So the relative min of f is what? Oh, it's negative 4. That's the lowest. That's the point, the y value of it. Okay, great. Okay, we can get to one more topic in this section before, no, I don't think I can. Let's just do another graph. Guys, I still have a lot in 2.2. I've got even and odd symmetry, and I've got piecewise functions. So I'll have to do those in the next class period. That's fine. Remember, it's not going to be Monday. It's going to be a week from Monday. So let's look at this example, and I'm going to go through the questions in the book and ask you all the things from this. So I made this example up already, and I kind of put the coordinates here. So this is negative 4, 1, negative 2, 3. I know it's hard to see. Negative 2, 3, that's 2, negative 3. And I'm going to ask you a lot of stuff here. And you can start filling in the answers as you go, or just wait till I get done. Either one is fine. But we're going to go through this with all the questions. So first I'm going to ask for domain. Then I'm going to ask for range, of course, that comes after domain. And then I'm going to ask for the X-Intercepts. And then I'm going to ask for the Y-Intercepts. Y-Intercept, I should say. And then I'm going to ask for the increasing, decreasing constant, A, B, C, D. We'll start it up here, okay? Increasing. Where's this thing increasing, right? Let me get a finer Sharpie. Increasing, A, B, C, D. Decreasing. Constant. Okay. The relative min and max, so I'm going to ask it how they ask it. And actually this has, you can see this has both. Now look guys, that is not a relative min. I'm going to stop here for just a minute. Look, that -4,1's not a relative minimum because we don't know what's happening to the left of it. To be a relative min or max, it has to be the highest of all the coordinates to the left or right, or the lowest of all the coordinates to the left or right, okay? Right here, we don't know what's going on to the left, so it is not a relative anything, okay? So I'm going to be lazy and just put relative min, question mark, relative max. And we're going to just word it as coordinates. And then A, B, C, D, F, G, H, I, J. Let's do, what is f of 2? Then, yeah, we'll stop there because the other stuff we just haven't got to yet. So I'm going to press pause. Okay, so I'm going to start working through this. If you're still working, that's fine. But let's look at the domain. I can tell you right now, look, this domain doesn't go forever to the left. It stops right here at 1, 2, 3, 4, right? -4. And then though it goes forever to the right because we're going up and to the right. So it goes forever to the right. Now I have to include the -4 because it's a closed circle. So -4 to infinity, boom. That's my domain, right? Range is a little weirder. I will pull out the marker for range. Look, if I think of this y-axis, the furthest down we go is -3 here. Do you guys see that? That's the furthest down we go, but we go forever up because of that arrow. We're going to go forever up. So the range for this would be -3 to infinity, right? The lowest we go is -3, and the highest we go is to infinity because, again, this arrow goes up. The X-intercepts, we actually have 2 of them, right? We've got 1 and we've got 4. Now we've got to write those, though, as coordinates. Okay, 1, 0, and 4, 0, because that's where we cross the x-axis. The y-intercept, we only have 1 of those. Look, we can't have 2 y-intercepts and it be a function, right? I mean, imagine this line had another y-intercept, okay? If this line had another y-intercept, it would fail the vertical line test, right? So you can only have 1 y-intercept. You might have none, but you can only have 1. That would be what, 0, 1? Right, for the y-intercept right there. So now let's go over the increasing, decreasing constant. Now I'm going to use some colors again. So increasing, I'll use blue. So if I start all the way here to the left, look, from -4 to -2, I'm increasing, you know, on the roller coaster. And then whew, I go down, right? You like the sound effects? I go down from -2 all the way to +2, right? So right here from -2 to +2, I'm going down. And then at +2, it switches to going back up. Hey, I get to use that union notation, okay? So for increasing, though, I've only got 1 interval that's, oh, no, I'm sorry. I've got 2 intervals that are increasing. That's my blue, right? Now remember, I never include endpoints for increasing. So negative, not negative infinity, it starts at -4. -4 to -2, I'm increasing. That's this blue interval. Then it hops over to +2 to infinity. Right? I am increasing from -2 to -4 to -2, or from 2 to infinity. Okay? And now decreasing, though, I've only got one interval. That's that red interval, right? -2 to 2, I'm decreasing. I am not constant. I'm not flat-lined at all, so I'm going to put a big circle with a line through it for the null set, okay? I'm not constant at all. I do have a relative min. I'm going to be lazy here. Remember, it's going to ask it weird, but I do have a relative min. It's at 2, -3, so it's, I'm just going to say 2, -3 to be lazy, okay? And then the max, though, the relative max is at -2, +3. Again, this is not a relative min because I don't know what's happening to the left of it, okay? Relative min has to be the highest or lowest. Yeah, Jeopardy theme is perfect. I just saw that. Relative min, any of the relatives have to be the lowest or highest for all the coordinates around it, okay? F of 2, okay, if I go, that means remember x equals 2, and I'm really trying to find what is y equal. Well, at x equals 2, go down here, y equals -3. That's the answer to J, okay? So homework for this section is going to be weird because I haven't hit like 2 of the main concepts. So I'm going to just chop it up a lot. If the homework asks you to find even, odd, or neither, don't worry about that. We're going to go over that on Wednesday, okay? And you'll see it like number 33 that we started. The very last part asked for is F even, odd, or neither. Well, don't worry about that one. Just skip that one, and I'll hit that on Friday. Okay. So for homework, though, it starts on page 239, and I want you to do 1 through. Let's do 1 through 13, and then I'm going to skip over I don't like the calculator stuff. So 1 through 13. And then 33. Now remember, don't worry about the even, odd, or neither. 33 and 35. Okay? And these are all odd here. Okay? Those are all odd. If you want to do the even, that's fine. If you want to do the even, that's fine. But those are all odd. I'm going to have to pick up, if you're looking in the book now, like 17 through like 31 talks about the symmetry. And that's what we're going to focus on when we get to class on Wednesday. Okay, so a few things before I just say goodbye. Remember, Friday I will not have office hours. Tomorrow my office hours are even kind of goofy because of this comprehensive exams. So if you need to talk to me, just email me. So not a big deal. Email me first before, and we'll find time. Okay, I've got time. It doesn't have to be my office hour. I'll make time for you. Okay. Okay. Any questions? Great. It's 3:15 or close enough. I will see you guys a week from now. Enjoy your Labor Day holiday. Hopefully the weather is nice.